Hi, everyone. Let me introduce myself. I'm Sarah. I'm data scientist at Data Scientist, and I will present to you today principal component analysis. That is a matter of great importance in data science and interpretability. I think we're going to have to wait just a little bit for everybody to come in. And if you have any question about data scientist, please feel free to ask in the chat. Today you'll be seeing me as a little icon in the video, and I will present to you the data workshop in the slides only. Then you guys have a chat where you can put your comments or questions, and I will try to answer to these questions either at the end, or if I see a question that pops in, I will try to answer to it in the middle of the presentation, but I'm not saying I will answer to all the questions during the presentation. So I guess that is the two, 1 or 2 minutes for this to start. If you have any question about data scientist, we remind you that data scientist is a company that enables people to have a training in data science, in data analysis, in data engineering, and that proposes a training on this subject through bootcamp or continuous training. And we also propose courses such as this one, but closest to the code. Today, I decided to present principal component analysis in order to make a little mathematical overview and to also answer the questions that we've had a lot in the master classes. That is our live sessions, live lessons. So I think I might start in just a little minute. You'll be able to find the presentation afterwards in the YouTube channel. You can click on the different documents that will be shared with you, if it hasn't been yet. And so I might now start with the presentation, and we are going to go to the part of the subject. So today I'm going to present a workshop on principal component analysis that will give a little mathematical overview and also an overview of the use of principal component analysis. The idea is that we've had a lot of questions on this subject and also in the interpretation of the objects used by principal component analysis. And this will be answered throughout the data workshop. I wish that you ask questions throughout the course or throughout this workshop, and I will try to answer at the end of this workshop. So feel free to ask on any kind of question that you have on the subject, on the slides, on details of the slides, and we'll try to answer. So, what is the difference between probabilities and statistics? Probabilities define the laws of theoretical random events. So that's theoretical random events. You have, for instance, the laws for the length of the wait at the bus stop, the probability of finding a king in a card deck, dices, the number of clients entering a post office, and the number of particles emitted by a gram of radioactive matter or material. And in probabilities, we can create samplings that would resemble our histograms that we're used to seeing in data science when we do statistics on our data sets. Now, there is a way to produce some of the probabilities as density curves. Here, you have an example of Poisson's density curve. And it is different from statistic in that statistic is the science of explaining or extrapolating with mathematical functions random empirical events. So that's empirical from experience, existing data. And the science of data is part of statistics. Now, we can see that, for instance, we have a histogram of minimum daily temperature. That is a graph that we can make owing to our data set. That is the data, the empirical data that we have. This distinction is important because PCA and data science in general will mathematically use statistics. Now, what is PCA? PCA is a linear transformation which takes the data from its original space into a new subspace with reduced dimensions, keeping the most explained variance possible. So we'll try to dive into this now, explaining the different words that were in bold. Space is a vector space on which dimensions are defined by unit vectors corresponding to our features. Here you can see that there's a coordinate system with z, y, and x. And this coordinate system represents the vectors that represent our feature or our features in space. So, for instance, if you take a data set with weight and then height, and then, for instance, uh, uh, the size of the cranium, you would have uh, a um, a point that you can put in a system of coordinates that correspond to our weight, size, or height, and cranium size. So now, what is a linear transformation? A linear transformation is a transformation of the space that is actually linear. You can find, for instance, reflection, scale, shear, projection, and in comparison, you have what is a non-linear transformation of space, that is this kind of transformation. So now, what is a subspace or a hyperplane? A subspace is a space in a space of n dimensions. So, for instance, n features. A subspace is a space that has fewer dimensions, so n minus k. In a hyperplane is a subspace that has n minus 1 dimensions. And here you can represent a subspace or a hyperplane as a plane in a 3-dimensional cube. Here, this is the plane that we're talking about, the subspace or the hyperplane. And here we can see it's actually a kind of LDA, it's separation of the variables through a hyperplane. And now you have what dimensions are. Dimensions are the number of features that exist into the data set. So if you take a data set here, we have different columns, different features with textual data, for instance, that you can transform into numerical data afterwards. And the elements would actually look like a matrix, look like this, where you have the objects that are the entries with the different values or the different experience of random events, and then the attributes that are the features of our data set. And it's a numerical matrix that you can plot in your n-dimensional space. Unfortunately, the human brain is not able to produce a representation of more than 3 dimensions. So if we take the three first features without doing PCA, we would have a representation in space that would look like this, that we can actually project on planes or hyperplanes, and in different hyperplanes would have different views. For instance, this one is a y and x, and this one is x and is z and y, and this one is the one that's left. So what now is variance? Variance is a measurement of how far each number in the data set is from the mean or the average, and thus from every other number in the data set. When you look at the approximate here, the approximate difference in the middle of distribution here or here or here, these lines would actually be the lines corresponding to the standard deviation approximately. That is the square root of the variance. The variance here has this formula, which is the sum of all samples xi minus their mean square to the power 2 divided by n, which is the length of the data set. And this variance will be you will be able to project your points in a single direction here, the red line, and you could compute a variance on this line between on the differences between of the distances between these points that you projected on your line. Now, what is explained variance? Explained variance, if we take this graph again, and we have another kind of graph that is similar to this one here. This is a direction on which you project all the points of your features, and you can compute the variance that is corresponding to this line. And the variance corresponding to this line is the explained variance of this direction. Now, if you take all your features, you will have a direction that is the direction of the feature. So if you have you have two axes here and here, you will be able to also project these points on these axes here, and it will enable you to compute the explained variance on these axes that represent features. So here it's feature 1 and feature 2. So feature 1 and feature 2 will, for instance, here, if you have only 2 features, if you have more than 2 features, will be the first 2 features here. And you will have the explained variance here for the first feature, and here the explained variance for the second feature, and etc. as the number of variance grows. And then if you actually add up the variance, if in descending order of the elements of the explained variance, then you would have a line that is a cumulative explained variance. So the cumulative explained variance basically is this cumulation here from 0 to 0.2 is the first feature. And then there's a feature that has an explained variance a bit less than 0.2 that you add up, and you will find yourself just a bit below 0.4. And you can go like this until you've added all the explained variance of all the features, and it will stand at 1 because it is a because it is the total of explained variance, the 100% of explained variance. So now if we take the definition again, it should look a bit clearer to you. PCA is a linear transformation which takes the data from its original space into a new subspace with reduced dimensions, keeping the most explained variance possible. So now if we want to look at what it looks like on a graph, we have dimension 1 and dimension 2 that are features. And we have a scatter plot that is plotted on these dimensions. If we try to find the direction where we have the maximum explained variance, this will be the line where you can see here it maximizes the explained variance, or the distances between the points on the projection of on the this line, which is the blue line. And then if you remove the part of explained variance that is in this projection, this direction, you will find another direction, which will be the part of explained variance that is left. And this is a mathematically an direction that is perpendicular to the first direction. So here we're missing a component 1, but that's component 1 here and not dimension 1. And here a component 2. So here we have the projection of the scatter plot on each of the components being the components associated with principal components analysis that we call principal components. And then we'll have these different points that will compute and explain the variance on the different directions. So now, why PCA? What do we need PCA for? We need PCA for dimensionality reduction. When projecting the data onto a new subspace, it removes the duplication caused by features that are very correlated. For instance, if you have a linear combination or almost a linear combination between the features, it's not useful for you to have these two columns in your data set, and PCA removes it for you. Then the dimension is reduced, fewer components chosen than the number of features. This means that you will have a computational cost that is lower because there is fewer data, because data is compressed. And the matrix representing our results as well will be also reduced. The matrix will become less sparse. You would have fewer zeros, and this economizes memory without losing information. So now, on other aspect of dimensionality reduction would be for high dimensional data when the number of features p is superior to a number of records n. So if we have this here, you have p, the number of features, and you have n, the number of observations. And you can see that here the number of features p is much higher than the number of observations. So if you look at, that's what the matrix again looks like in each of the problems. And here you can see the different domains or industries in which you can find high dimensional data. So for instance, you have the financial markets, where you have PE ratio, market cap, trading volume, dividend rate that is aggregated to your data set. You have healthcare issues, where you have blood pressure, rating heart rate, all medical records for a person in different aspects of his body, immune system status, surgery history, height, weight, existing conditions, etc. And you also have genomics, where data for all genes and versions of an individual that are, for instance, 25,000 genes, and you have two versions of each version, and each version, sorry, has its own set of values. So the modes that we would call in data analysis. And if you imagine encoding on each value, you would have more than 75,000 records for three values of each gene. 75,000 records for 10,000 patients. That's a number of feature that is much higher than the number of records, for instance. And when we have more features than observations, we might overfit our model on our training sets, and our evaluative scores would be too low. So for instance, the predictions would not be accurate enough. Now, there's another aspect of this. It's the curse of dimensionality. When increasing dimensions, the matrix representing our data is often sparse. There's a lot more zeros than non-zeros values. and it makes it difficult to train. Wikipedia states that, as a typical rule of thumb, uh, there should be at least 5 training examples for each dimension. Here, the average expected predictive power of a classifier or regressor first increases as the number of dimensions of features used is increased, but beyond a certain dimensionality, it starts deteriorating instead of improving steadily. What does it mean? It means that uh, if you increase the number of feature in a certain in a certain way until a certain number of feature, the prediction performance increases. Then, if you go on increasing the number of features, the prediction performance decreases. And that is actually very important because as PCA reduces dimensions, we will stay in this step where you have uh, uh, the maximum prediction the maximum prediction performance for our algorithm. There's another observation that for a simple classifier, both the size of additional features and their relative cumulative discriminatory effect are important in observing a decrease or increase in the average predictive power. So now in data mining, for instance, if you have an association rule of genes, you would have the complexity of these algorithms can lead to calculating all permutations of gene pairs for each individual or row. And given the formula for calculating the permutations of n items with a group of R, of a size R, sorry, you would have n factorial over n minus R factorial uh, increase in the number of pairs. So for instance, if you're calculating the number of 3-pair permutations of any given individual, it would be more than 7 billion different pairs of gene to evaluate for each individual. And it's actually a lot of data. So in clustering, if the data has too many features, it makes it appear in our space equally distant on a Euclidean distances viewpoint. And as our algorithms use this distance to make its calculation, it makes it impossible to produce clusters. It's as if your algorithm was seeing this red point surrounded by all these points in equal distance, and you wouldn't have this idea that these points, for instance, are further away to these points than the points that are in the same cluster. Now, what do we need PCA for? We need PCA for also, and that's very important, interpretability. We have visualization of the strong patterns in the data set, and we also have interpretability of what the principal components are in reality. So, for instance, if you take here this example of the circle of correlation, you have a kind of clustering of disciplines of Olympic Games in athleticism. And you have a correlation here that is presented in the run or the 400-meter and 110-meter hurdle and 100-meter, sorry. And you have another correlation of jumps, for instance, long jump and high jump are gathered. Now you can see that there's a lot of different representations that you can make. So for instance, here you would have a representation according to uh, the distance also, but that's the same kind of representation. Here you have clustering, here you have the cosine distance, and here you have the same kind of distribution, but for the athletes. And here you have another graph with the contribution of the 2 dimensions on each of the athletes. And here, this is something that's a bit different. It's a clustering using PCA of plants of plant recognition. So after that, after feature selection, we have what? We have to drop features with many non-values. We can drop features with low variance that have very similar value. We can drop features with weak correlation with the target variable, and we can do PCA before inputting in our algorithm. So now we're going to look into the math of the object. Principal components, as we said before, is just a linear transformation of our basis of our features. And here you can see that if you rotate this graph, you will find a new coordinate system that will represent our clouds of points in a way that is more fit to the explaining of the variance. Now, if you look at the different elements that we will need for our explanation, you have sigma, the empirical covariance matrix, which is symmetrical and is also diagonalizable for this reason, and lambda, the diagonalized covariance matrix, gamma, the base change, and sigma will be equal to gamma lambda gamma transpose, where gamma is the a diagonal matrix. So the empirical covariance matrix is here. You have variance of x1 being the first feature and covariance of xn, x1 being the covariance of feature n and feature 1. And you will have also an important fact that your matrix here is empirical variance and not the variance of the random events. So now if you look at our vector x, x is a vector where you have the p features and here the number of records. So these are this is basically the vector that is corresponding to our data set. So if you have an application or a transformation in space of n dimension or lower, you would have this transformation that for x gives y, or it could also be e space that is n dimensional and not necessarily r to the n. And it would be y is equal to f of x. The matrix associated in this space will be m of f, and you would project this matrix in a certain basis. So here we choose a basis E1 En, which is a base that is an orthonormal base. For instance, E1, E2, E3, and you have Ek being equal to 1, the norm of each of the vectors. Here is 3-dimensional. And our matrix will be m of f times x will give y our targets, for instance. And you would have in a 2-dimensional space E1 and E2 that would give x, for x would give y with the f function. Now, if you make a base change, meaning if you do the 45-degree rotation, for instance, that is a linear transformation, to our vector unit vectors E1 and E2, then you would have new vectors that are gamma 1, which is, and this is not really important, but say that it's a linear transformation or a linear concatenation of our vectors. Here it's square root of 2 over 2 E1 plus square root of 2 over 2 E2. And here it's gamma 2, which is equal to gamma 2 over 2, square root of 2 over 2 E1 minus square root of 2 over 2 E2. And the base change would be the projection of our vectors, gamma 1 and gamma 2, on E1 and E2. And this would be the matrix of change. Now we can also write our matrix, MF, in another base. That is the base that to which we changed. And there is m of f in gamma 1, gamma n. And you can see here the projection of f of gamma 1 and f of gamma n on this new basis. The matrix will then change. And this is how we compute the lambda matrix, that is the diagonalized matrix of covariance. And you would have here the diagonal values of the diagonalized matrix that are the eigenvalues with the share of explained variance. And this would be a matrix written in the gamma k base, that is the base change. So you have gamma 1, gamma n here, and f of gamma 1, gamma n, that is this matrix here. And if you look at the covariance matrix, you also need to change the base in the first place to find this lambda matrix. So you have gamma, lambda, gamma transpose, which will be the matrix of covariance. Why is this important? Because the principal component here, and that's the heart of the matter, is one of these gamma k. And the first component is gamma 1, being here, the first eigenvalue that is ordered by descending order. And here it's the maximum of the eigenvalues, and it corresponds to the maximum of explained variance in the first finding the first PCA. So now gamma j is equal to eta j, is equal to gamma j transpose x minus mu, and there's a projection on base for diagonalization of the vector x minus the mean of the random sample, and it's the solution or the argmax of max of var of a transpose x minus mu, where a is in is a vector of this space where the norm of this vector is equal to 1. So that's basically the vector that maximizes the solution of this equation, and it's a vector that is called the first principal component. And when you have a base, for instance, the x-axis, the new x-axis will be this vector specifically that has an explained variance to the problem of the value of lambda 1. This is the first eigenvalue. So now if you want to look at the second principal component, this would be the solution to the same equation removed the variance of explained variance. Then if we want to, so these were the introduction to the mathematics behind what we have in PCA. And it's actually important to understand because once you get this, you will understand how to interpret the graphs that you have in PCA. Now, how do we code PCA? Let's leave the math on the side and go into the code. We have different packages that will actually present the PCA. You have stats model that will use the multivariate.pca module, and that will just be instantiated with PCA x and n components. So that's the number of component max that you want to keep in your PCA. And you can use different attributes such as eigenvals that will print the eigenvalues or in descending order. So you see here the first eigenvalue is 5,152, and here it's 192, and here 171. And there's also sklearn. So for instance, if you take sklearn.decomposition, you will import PCA from the decomposition module, and you can use PCA instantiated with n components is equal to 3, but you can actually add as many components as there are features. And you can also put an explained variance ratio that would be, instead of asking to keep 3 components, you would ask to keep that many components that would enable you to reach the variance ratio. So now, if you have another element that you could find from these PCA packages, it's PCA.explained variance ratio, which enables you to see the variance ratio of each of the components. And here you can see that there is, for instance, the first component as an explained variance ratio or an eigenvalue or more an explained variance ratio that is 0.9. So the first component here explains most of the variance of your data set. Here, if you want to print a cumulative variance, which was the curve that we saw earlier with a staircase, you will have PCA.fit, so you fit the PCA on your data, and then you try to find the cum sum, the cumulated sum of PCA.explained variance ratio. If you want an explained variance ratio not to go over 0.95 or 95%, then you will cut this short the uh, to the coordinates 0.95, and then you will find here that it's approximately at 23 the number of components that have been uh, the number of components that could be chosen for your study. And you see that it goes till approximately 62 components. So you reduce the data set by approximately 40 columns. Now, what about the interpretation? You can draw a circle of correlation, which is an element that has a link with correlation coefficient. So the Pearson correlation coefficient is the covariance divided by the standard deviation of each of the features. Now, if you project these arrows that represent the feature in the circle of correlation, and the different axes that correspond to the components, the first components of the PCA. Here you have component 1 and here you have component 2. If you make the projection on each of the axes, you will find the correlation between the feature and the component. And if you do also the projection of each of the features onto another feature, then you will find the coefficient of correlation between the two variables. And it's the cosine of the angle between the two variables. Now, if we do a recap, we have the order of explained variance that gives you the order of the principal components on which you have the decomposition of your new base, which is classified by order of decreasing eigenvalue, that is to say, by order of explained variance associated. In general, we only take the components whose sum in decreasing order is lower than a chosen limit. The variance limit explained depends on what you want to choose on the case you're working on. So if your prediction is accurate enough with the variance threshold you have chosen, then this is good enough. For example, there are diagnostic problems where you want the predictions to be extremely precise, and in which case you will adjust your choices according to this. The very nature of the choice is subjective, depending on the quality of the subject. The two axes correspond to principal components, which are the first two in the order of explained variance, and which are a priori explanatory variables, which do not exist in your dataset, but which are indeed linear combination of your other variables, and that is actually very important. And the axes are the axes of the first two principal components, but in different spaces, or the space of explanatory variables, or the space of targets. Reducing the dimension amounts to reducing the number of principal components by making a choice on the explained variance threshold. And on the circle, the two axes correspond to the first two principal components. The arrows, they correspond to the real variable projected in the space of the principal components with their correlations according to the two other variables, positively or negatively, with elements of norm which correspond to the coefficient of correlation of the real variables with the principal components. The corresponding vectors are, as in a change of base, the projection of the representation of the initial vectors, and the two PCs being the new base. It's a bit of a chunk of text, but this reminds you of everything that we've seen earlier in this presentation, and that are key points for you to understand when you use these correlation circles, for instance. So now, what are the drawbacks of this PCA? For instance, if you take a PCA on a signal of a stock market or prices, here you have a problem of interpreting the first component, that is the black line here. You could ask yourself, what is this component? And here, or what is it linked to, for instance? What does it represent in reality? So your intuition could be, this represents the overall general stock market, and you will have to uh, compare it to the stock market. And great, here you can see that it's 90% corresponding to the stock market. And for the first component, so you did an interpretation of this PCA. But for the second PCA, you have no clue, and you look at, for instance, component 3, or second or third, and you have here a difference between the component 1 and the component 3, and it's actually very different from the stock market. And you don't see if you have other features or other elements that are of the domain that would look like this curve. And now you're facing a problem is the interpretation of of the principal components that we're looking at, the principal component 3. And this could actually be an issue for a lot of different domains. If you're looking at meteorological data and you're looking at, for instance, the curve of humidity, or if you're looking at the curve of temperature, but another, for instance, if you're trying to look at the curve of temperature at the surface of the Earth instead of looking at the temperature at higher altitude. So that is one of the drawbacks, and the biggest drawback actually of PCA. Now, if we recap in dimensions, you have a problem in 2D where you have the explained variance and the eigenvalues and eigenvectors. Then you have a circle of correlation that looks at the correlation between principal components and also the different existing features. Then you also have the possibility to cluster. So meaning you create a PCA and then you input this in a clustering algorithm that will enable you, or just sorry, not clustering algorithm that would find the centroids of clusters created through a graph of your PC1 and PC2 that you wouldn't have found if you had not done the PCA. Because the representation would have been different, as is probably in a higher dimensional space where you can't find a pattern. So that is what we can do. And for instance, you can use here the k-means algorithm. In 3 dimension, it's actually all the same, but it's more fun. So that's my idea of things. And you have in 3 dimension the possibility with for instance, plant recognition data set here to have clusters using PCA and projecting the elements in the first, second, and third eigenvector. Now, there is this website that I wanted to show you because I think the representation is quite fun. You have an example in 3D, and you can see here that there are several elements that fit easily a PCA. It's actually like a straight line in a 3-dimensional space. And now you also have, for instance, the circle of correlation that were represented as a sphere of correlation in 3 dimensions. You have a way to first present the correlation of each of the variables according to the different. So that's a heat map, but you could do the heat map also with the dimensions of the PCA. And you have here, for instance, in water and sediments, the correlation between the different ions. So here you can see, for instance, that in sediments you have lead, sorry, and copper that are well correlated. You can see that because in sediments they're in the same direction of the second PCA. That means that they are positively correlated with the second PCA. And you see that, for instance, the Hg, mercury, is also positively correlated with the third PCA. And you have cadmium, which is negatively correlated with the third and the second PCA. What does this mean? If you have a high value on the lead, you will have a high value on the second PCA. And if you have a high value on the cadmium, you will have a low value on the uh, PC2. And when you look at the PC2 or at the graph of PCA, uh, the 2D graph or the 3D graph, it enables you to say where, with this circle, you're going to find your points in the PCA graph. And reciprocally, but with more difficulties, because you have on the graph three dimensions at max, and you would have on the circle of correlation all the features dimension as correlation. So now in n dimension, as you can't make a representation that would be understandable by the human brain, you can either project in 3 dimension or use the cumulative variance that we saw earlier. So now, what are the alternatives? You have linear PCA that, as we saw, is made for linear cases and numerical features that are quantitative or continuous. And you have also other PCAs that are for high volumes of data and also nonlinear cases. You have randomized PCA. Randomized PCA to get a random subset of your data if the data is too big. And then you use SVD solver in your PCA and write it at randomized. Then you have incremental PCA that uses batches and makes a partial fit on each of the batches. And you have probabilistic PCA that would sorry, and you have also probabilistic PCA that uses maximum of likelihood, but that's actually lots of math now, and we will not go into the detail of probabilistic PCA. Now, there are also nonlinear cases where you would have, for instance, kernel PCAs. Here you can see you can project the PCA on a circle, but you can also project these data, that is a Swiss roll, onto kernels, linear kernels, or RBF kernels that give PCA with kind of clustering that look actually like this. So that's the transformation of this element into these element through PCA. It's possible to be tuning parameters also with different kernels with grid search. If you say, I want to try linear kernel, RBF kernels, and other elements from the different kernels that you have for PCA. Now you have other interpretation elements that are not PCA but that are close to PCA. So for instance, if you take multiple correspondence analysis, if you use the chi-square tests, you will have something that is for specifically categorical values instead of having quantitative values. And you can see in the correspondence analysis here, and that's very used in marketing issues. You have, for instance, the representation of salary according to the use or the sale of a device, technological device. So here you have, for instance, for less than 30,000 euros of salary, you have a laptop computer that would not be a Mac computer. And you can see here that's the space that is actually closest to this salary. And if you look at here, you would actually have in higher values of your salary would be a Mac computer, laptop, iPod, iPhone. And for middle income, you would have iPad, PC, and Mac computer, desktop, and not laptop. Now, if you look at this test, you can actually plot what represents or make a graphic representation of a moon plot. So if you take another correspondence analysis where you have for each of the brands, Diet Coke, Diet Pepsi, Pepsi Coke, Coke Zero, and Pepsi Max, a sentiment analysis that is associated with it and with a lot of different words. Here you can see that, for instance, up to date are beautiful or closest to Diet Coke and Diet Pepsi. And individualistic and humorous are close to Pepsi Max, for instance. The distance between the different words, either a cosine distance or a Euclidean distance, represents somehow a semantic closeness. And here we can actually plot it in a kind of moon plot that is actually pretty, or very pretty. And you have Pepsi Max, Coke Zero that are close to rebellious, for instance, and Coke Pepsi that are close to traditional, as Diet Pepsi and Diet Coke are more like feminine. And I actually, it's a sentiment analysis. I actually agree with this analysis, but it's a sentiment analysis, so it's very subjective to me if I give my opinion on the matter and not on the statistics. So now there's also something else that is called MFA. In statistics, you can use MFA, that is called factor analysis of mixed data, or factorial analysis of mixed data. And this multiple, sorry, this is what is what it is when you have the active variables belonging to two types of data, meaning quantitative and qualitative. And this you will add to a PCA, that is for quantitative variables, and a multiple correspondence analysis, that is for qualitative variables. These elements will be used in what we call a multiple factor analysis that will do that is a multivariate method that will surround all the elements in your dataset. And then what we have also is what we call ICA, that is in signal processing independent component analysis. That is a computational method for separating a multivariate signal into additive subcomponents. So, for instance, if we have this signal that is composed of three different signals, we have a separation of ICA, that is this separation. These are the recovered signals. And this is the true source. So this actually pretty close, because the red line is like the orange line and the staircase is like the blue one here. And also the rectangle is the red one. So they actually retrieved pretty well the signal, as PCA did not recover that well the signals, as we can see here. So this is ICA. And here we also have another kind of study, that is a manifold with a TSNI or a TSNE, sorry, or isomap. So for instance, manifold is a surface that is folded in space where you can find clusters for your data. And there are several elements that you can apply to your manifold that would project into different components and find with more or less accuracy clusters. So if we make a comparison between the different methods, here we have principal components projection. So that's the first one, and it looks that it's clustered, but it's a bit messy. Here we have isomat projection of the digits. Then we have linear discriminant projection of the digits. And here we have TSNE, embedding of the digits. And the TSNE is the best method that would enable you to cluster your data on a manifold. So now, what to do with PCA? You can do PCA for all industries, for all types of data, and also for all types of formats of data. You can use it in sensory data, in surveys, in multidimensional text mining, in signal, and in video. But you can also, in video. And you can see here that, for instance, for the digits, we're compressing the digits. We can find a decomposition of the digits PCA on the first component here. And each of the elements will be aggregated in the components will be aggregated on the images. And at the end, you will find your image, for instance, with, I think, maybe fewer features that you would have in the beginning. And it would look like a 9 when you start the 300 at 300, the number of components. Then you also can do this with face recognition. here are some vectors that are eigenfaces. So for instance, these are the first components of the eigenfaces that you have in your data set. You can do this with signal separation, and you can also do this, that's actually a well-separated signal. This is a separated signal of symbols. And then you can also do this with semantic closeness of different words. So that's something that's closest to correspondence analysis. And here you can see that you have an element of, for instance, aesthetic, viewpoint, and sensory other are close to together, and you have cloud dimension categories that are close to that are close that are close, and then you have, for instance, property link. Barycenter eigenvalues correspondence that are close together, and this is actually they put the words that are corresponding to PCA, MCA, CA, and clustering. And you see that there are clusters of values. For instance, PCA and MCA are close together, and clustering and CA are, and clustering is far from this group of data. Now, if you look at PCA in remote sensing, so that's actually you're getting into, for instance, more scientific elements. You will have eigenvectors here, and you will have principal components that have a big part or a big correlation with some of the different components. That would be brightness, gritness, swarmness, etc., and bands of frequencies that correspond to the remote sensing from the satellite. And here you will have, for instance, if the PC2 is corresponding to number 4, I think it's greenness, or PC1 to brightness, then you will have the representation of the picture under this um, under this angle, or not angle of taking the picture, but under this filter of brightness or greenness or stormness and wetness. So now, these were examples of elements that you can use PCA for, be it different industries, be it different types of data or formats of data. But it's all about the features, the whole column of features. And you have also another type of interpretability, and I'm just opening here on the fact that with SHAP values, you can take a single record in your data set and find the actual explained element that corresponds to the explanation of the value for this feature associated with the output. So it means that, for instance, here, hormonal contraceptive would explain a certain part of the value of our element with a positive or a negative impact on the value of our element. Uh, so now, as a conclusion, I will say that PCA is a very good dimensionality reduction and interpretability and visualization tool. PCA is easy to code and integrate in your algorithms. The math behind it and the interpretation is not rocket science. There are several alternatives according to the types of data that you encounter. Its use spans on all industries, domains, types of data, and formats. And it's a great tool to open really meaningful analysis for real world data, like dreamlike issues on remote sensing, interpretation, medical data, signal processing. So now, if you start using PCA owing to this video, please have fun. And remember, you can't make everyone happy. You're not PCA. Do you guys have any question on the matter? I will leave this page, go back to the StreamYard, and look at your different elements. So I'm looking at your questions. I'm sorry, the graphs were too small. I apologize for this. I think you will see the different graphs on the recording. Most of them were to actually see the pattern more than to see to see the actual values inside of the graphs. Quantitative? No, you have to have the so there's another question here. Must all the features be quantitative, or can a part of them be qualitative? They should all be qualitative, but you can use, for instance, a correspondence analysis or MFA for these to be used as an interpretation tool. Let me just take a look at this element. Now, another question. Expand the connection. Uh, I'm looking at one of the question here. And I will look at the other question after this one. So the difference between PCA and factor analysis is that factor analysis takes both into account, or multiple factor analysis at least, and you would have MFA being the junction of all these analyses. How can you recompute the this is actually according to what you need to avoid sparse matrices. I think if you really want to avoid sparse matrices in your data set, there's actually a mathematical computation to be made if you already know the zeros and the dimensions of your matrix. But I think this could be a complex computation. Otherwise, if you're looking for a certain type of accuracy score in your prediction, you would actually be able to find the optimum values according to the experiences that you make in your number of components in the PCAs. That could actually be a hyperparameter in your algorithm. Um, is there an example code that represent the circle of correlation? An example of code that represent the circle of correlation, of course. We're going to go on the train website, and we can go here. Uh, Introduction to ACP. I will look into this while it's loading. Here, PCA, it's the same thing. You can actually reduce dimension. Sorry, in hi Hans. In text mining, you can actually also reduce dimension. So I get this is also the advantage in text mining. What we do in text mining is something else that is called word to vec, for instance, where you create a matrix of embedding that also reduces dimensions in your sample, and that enables you to have a matrix that is actually less sparse, because in text mining, for instance, you would create vectors that would input a 1 at the place where you have a and at the place where you have a the occurrence of your word, and it would be vectors that have 0 1 0 0 0 0, for instance. And through word embedding, you actually create matrices that enables semantic closeness, and uh, that you would multiply with your element in the space of the matrix. Yes, you will get the slides. I will give an example. Do we use PCA? Yes, you can actually use PCA with neural networks, I think. Okay, so if there are other questions, please feel free to ask now. Otherwise, I will try to answer for the code of a circle of correlation. Uh, so what I can say on SVD is that SVD gives you the whole 9 yards of diagonalizing a matrix into special matrices that are easy to manipulate and to analyze. It lays down the foundation to entangle data to independent components, whereas PCA skips less significant components. And now I will go for the code. Yes. So here is, sorry, the code. So let's try to take a look. Circle. Now, if we want to draw the circle of correlation, we will have this code here. If you all can see this, it's taking the square root of explained variance. So that is an array. And then you would input the PCA.components, the K components, with all the columns. So that's the K entry multiplied by the square root of the eigenvalue of the K element. And then you would plot this as a figure and axis, plt.subplot. And on each axis, you would set a limit of between -1 and 1. So that's for the unit circle. And then for j, in the range of the number of components, so we chose 9 components or 8 components, you will create an annotation that is for the column, the feature j, and you would present the name of this column, and then you would also create an arrow. So that's the arrows that we've seen earlier, and the arrows would have the size that would be sized with the size of the square eigenvalue here. That would be the core var of the j element here. That would be the number, the order of the eigenvalue or the explained variance. And then you will have to just plot these elements. So here you plot the 2 lines that are the horizontal and vertical line corresponding to your PCAs, and an artist, so a circle where you have the circle of correlation. And that's all you need to do. And I will go back to here to see if you can't see the code. I'm sorry. So here is going to you're going to have the code in another window. I thought you were seeing this through uh, present. So if you stop the screen and try to present the slides, the share screen, I will go back here and explain it again. So this is the square eigenvalues NumPy array. So this is PCA.explained variance. And you have for all the eigenvalues, k, a new array where all the columns at the k or the entries at the k column, sorry, will be the PCA component k times the square eigenvalue, the square root of the eigenvalue, which is actually the standard deviation corresponding to the part of explained variance for the k components. And then you will have figure and axis for a subplot. You set the limits of this at between -1 and 1 because it's the circle of correlation. And for j in range 8, so that's the number of explained of components that you chose, you will make annotations of each of the arrows. So for instance, here that's the name uh, of the feature j, and here it's the name of the and here will be the arrow corresponding to the value of the elements here, and this is this is the coordinates for these elements. And here you will have the plot of the two lines that correspond to the PC1 and PC2 that are inside the circle of correlation. And here you would have an artist that is a circle where the radius is 1 because it's a unit circle, and that's the code for the correlation. The correlation circle. And if we go back to the presentation here of the correlation circle, here, you can see that we have this unit circle, and that you have the projection with arrows and annotation of the different features inside the two dashed lines that are our principal components. And you have the here dimension 1 and dimension 2 that are representing the percentage of explained variance. So here that's 38%, and here that's 19%. And if we go here, uh, can you scale it? I'm sorry. Do you want to scale the code bigger? Um, Uh, so I have a question by Franz Gerbig. Would you mind? Would you please mind telling me if you want the scale bigger for the code or for the correlation circle? I guess that's it for the questions then. Uh, so thank you very much for listening. I think if you have any other question, you can ask it on the chat, and I'll be happy to answer to these questions. I will leave you now to PCA, and hopefully you will have fun in using this tool in the future. I will end the broadcast, and thank you very much for listening.